Okay, this is number 4 from the 2013 AP Physics B exam. This is primarily going to be a mechanics-based problem, and we have a 0.3 kilogram cup of negligible mass attached to a block of mass M on the table. String is connected to a pulley with another object hanging from that pulley, and then we're going to release that big mass from rest. That's going to accelerate to the right, and after moving 0.95 meters, hits a bumper, launching the ball horizontally through the air to the floor, which is 2.4 meters below the surface of the table, and it's going to land 1.8 meters away from the base, which is where it leaves the cup. And so for A, we want to know the speed of the ball just after the block hits the bumper, and then right before it leaves the cup. Right after it leaves the cup. And so a lot of students try to analyze the first part of the situation to figure out how much speed it gains during the 0.95 meters. And that's not really the best ideal way of doing it because we don't know the mass. There's just too many unknowns over here. So what we're going to do is look at the kind of the projectile motion that's happening during this segment. And during that segment, we have an object that's falling 2.4 meters, and while it's falling, it's also shooting forward. And so our ultimate goal is to solve for Vx at this spot. What is Vx? In order to find Vx, we need to know our acceleration in the x dimension, which you may recall is always 0 for an object that has no force. And there are no forces in the horizontal dimension. We need to know our x distance, delta dx. We do know that. That's 1.8 meters. And we're going to need a third variable to solve for every other variable, and that one's going to be time. So we need to figure out how long it takes to fall. And so for that, we're going to analyze my y dimension. We're going to recognize that my initial y velocity is 0. I know that I have a y acceleration. That's going to be g, which is the acceleration due to gravity. We also have, and I'm going to treat down as positive, so we also have a y distance it falls, which is 2.4 meters, and we can now calculate the time it takes to fall. For that, I'm going to go ahead and use the change in distance in the y dimension equals VIYT plus 1/2 GT squared or AT squared. I know VIY is 0, so VIYT is 0. I can rearrange this for time to show that the time is going to be the square root of 2 delta dy divided by g. And so at this point I can plug in my numbers. 2 times 2.4, divide that by 10. And I'm going to go ahead and calculate this. Of 0.69 seconds. Some of you would have used 9.81 for that, and if you did, your time would be a little bit larger, probably 0.7 seconds. Now, of course, that's not the end of the problem. We now need to recognize that time because it's a scalar term, exists in both dimensions, 0.69 seconds. And so now I do have all of the variables I need to have. I can solve for x by using the average velocity is distance over time equation, and that's what I'm going to do. So the average velocity is Vx because it doesn't change, which is equal to the change in distance in the x over time. We have both of those numbers. It's just going to be 1.8 meters divided by 0.69 seconds, which equals 1.8 divided by 0.69 is 2.6 meters per second. And that will be the answer to part A. And A was worth a total of 3 points. Okay, now for part B, we want to know the acceleration of the block as it moves across the table. And we're assuming the acceleration is constant. It is constant. This object is following, pulling the object, the whole system to the right. And so what is the acceleration? And again, a lot of students want to look at, they want to analyze the actual motion of the object, but they really can't. What you've got to do is instead analyze your kinematics here. We need to look at, well, let me write this down, B. We need to recognize that starting from rest, so my initial velocity is 0. It eventually achieves a velocity of 2.6 meters per second. Something is causing it to accelerate. That's what I'm looking for. And I know that it does this over a change in distance of 0.95 meters. I think this is the most appropriate way of solving for this one. We're going to go ahead and use the final velocity square equals your initial velocity squared plus 2a delta d. And I went and changed my i's, or my 1's to I and my 2 to f, and so you might want to use the right subscripts that you wrote down. v2 squared equals v1 squared. At this point, I'm not too concerned. Your acceleration is therefore going to be vf squared. Normally I'd subtract vi squared, but that's 0. All of that divided by 2 delta d. And so it's going to be 2.6 squared divided by 2 times 0.95. And I get a value here of, hold on, I did not square it. Pay attention to your square term. Don't do what I just did and actually square it. So it's 2.6 squared divided by 2 times 0.95. And I'm going to get a value of 3.55 meters per second squared. And that is the acceleration for Part B. Part B was worth 2 points. And finally, Part C, or I guess not finally, next, Part C. We would like to know the mass of the block. And here's where we actually get to look at the first part of this diagram, or what it looks like the first part of this diagram, and it's the whole, really the whole thing. We got to look at the dynamics of the situation here. Now, if we look at what's hanging from the pulley, we've got one object getting pulled down equal to its weight, mg. And there's a rope pulling it up, and then there's a pulley that's basically to reverse that direction, meaning that that weight is actually pulling the big block with a certain force to the right. There is no friction. And sure, there are forces up and down, but that's not going to affect the horizontal motion. So looking at just this x dimension on that big mass, we only have one force acting on it. So let's analyze our dynamics. The net force acting on the big block is equal to the block's, well, I'll come back to this, but it's going to be equal to ma, which will equal the one and only force pulling it to the right, which is actually this force pulling it down, and that's going to be mg. Here's what we got to look at. These m's are not the same masses. And so let's understand the way the system works. This block can't accelerate any faster than the big block, meaning the whole thing's going to accelerate at the same value together. The big block, the little block, the cup, they're all going to accelerate at a certain value. So this m may have better been written as, oh, I don't know, quantity m or something of this nature, because really, this m is the mass of the little object getting pulled. It's the mass of the big block. It's the mass of the ball. And if the cup had any value, it would be the mass of the cup as well, but fortunately it doesn't. So all three objects will accelerate at some value a. And they're going to accelerate from the one and only force acting on it, and that's the weight of the little object pulling it all down. So if I increase the weight of the little object, the entire system would accelerate more. If I decrease the weight of that little object, the acceleration would be less. So I'm looking for big M. I have everything else. Now, I'm going to divide my A term over. I'm going to add my M, little m terms. And we're gonna have big M plus 0.3 plus 2.5 or 2.8 equals little m naught, our object, divided by its acceleration. So then I need to subtract that 2.8 term. I'm going to go ahead and plug the rest of my numbers into. So I'm going to have, well, the little mass was 2.5 times g, so 25 is its weight. Divide that by the overall acceleration, which is what I already calculated, 3.55 meters per second squared. And this entire term, I've got to subtract 2.8 from it. And I'm going to get a mass of 4.24 kilograms. And part C was worth 3 points. Now lastly, we're at part D. If the mass of the ball is increased, the horizontal distance it travels when it hits the floor will decrease. And so why does this happen? So if I make this ball more massive, I know you're often taught that the mass of the object doesn't affect the ability to fall or the rate in which it falls. And that's all true. But it will affect its final speed it gains, because now this force, mg, which has not changed, is indeed going to be pulling more mass. And so this part here goes up. And as a result of it going up, and mg over here staying the same, a has to go down. So the acceleration, or the net acceleration of the system, decreases, and as a result, the final velocity of the ball just hitting the bumper decreases, and as a result, the distance it travels forward as it falls down will also decrease. I'll let you play with the wording on how to write that out, but it's only worth 2 points. One for indicating that it does decrease because the acceleration drops, and another one for stating that its launching velocity will drop as well. Okay, all done.